So today it is really great to have our very own Melvin Leok, who is a professor in the maths department, to give the TILOS seminar. Welcome everyone. Melvin has a very broad research interest, but they're all related to geometry. His research interests are computational geometric mechanics, computational geometric control theory, discrete geometry, and structure preserving numerical schemes. And he's also interested in symmetry, in particular how this subject relates to systems with symmetry. So Melvin has received, it's a very distinguished career. I see a lot of awards listed under Melvin's name. He graduated from Caltech with a PhD in control and dynamical system. He has been 3 times NAS Kavli Frontier of Science Fellow. He's a Simons Fellow in Mathematics. I think that's a recent thing. He has received the DoD Newton Award for transformative ideas. He received the Career Award, the SIAM Student Paper Prize, and the Leslie Fox Prize, among many other things. So we are incredibly happy to have Melvin here today giving the talk. Melvin, the floor is all yours.
All right. Well, thank you very much, Ari, for the introduction. So today I'll be talking about some of my work on discrete numerical methods, in particular discrete geometric mechanics, and how they impinge on ideas from information geometry and how they relate to accelerator optimization and machine learning. And so this is joint work of Valentin Dorițiu, who's a graduate student here at UCSD, Jeremy Smith, who was a former student of mine, and Jin Zhang, who's a professor of psychology at the University of Michigan. So let me go right ahead and give you some motivation for what, why one might be interested in this. So I'm particularly interested in a situation where you have a system which has both information and physical layers. And the tendency, it's like when one studies these kind of problems, is to view this as a layered or hybrid system where the information processing is done in some sort of discrete time setting, and then the physical dynamics is described in continuous time. So, and what usually happens is that there's an assumption that there's a separation of timescales, in the sense that we tend to optimize the information gathering aspect at the high level, and then we assume that the actual trajectories which that generates can be realized sort of efficiently in continuous time. So the problem is that this is suboptimal because in many applications of interest, there isn't this separation of timescales between this information and physical dynamics. So what we're going to try to do is to use ideas of information geometry and discrete mechanics, and the hope is that one can apply this sort of notion of backward error analysis to realize a class of machine learning algorithms as the exact time H flow of a continuous dynamical system on the space of probability distributions. And then this allows you to have a unified treatment of what I'm calling information mechanical systems, or cyber-physical systems if you prefer. The application I have in mind here are, it's like a swarm of drones. So if you have these drones, it's like, and they're part of your sensor network, it's where they're collecting information sort of on the ground. Then one application, it's like, which is of great interest, is this idea of using drones to perform reconnaissance inside buildings. And the problem with doing that, especially in a contested environment, is that you can disable drones quite easily by throwing blankets at them. So they actually need to fire pretty fast in order to avoid that kind of adversarial attack. And so typically it's like we're talking about something like 10 meters per second, or about 22.4 miles per hour in order to avoid this. So you can imagine it's like this drone sort of zipping down. It's like the corridor, it's like it sort of flies past an open door. And suddenly you have this new wealth of information which is available to it. And in light of that new information, it may want to respond to that by changing its trajectory. So in those kind of situations, it's like the new information is coming in, it's like at a sort of time scale which is comparable, it's like to the capabilities of the drone in terms of how fast it can move. And so one can't really assume that the information theoretic aspect is independent from this the physical constraints it's like of the drone flying. The upshot of this is that the information gathering aspect and coordination of swarms of drones could benefit from a unified treatment of both the information layer as well as the physical layer. Okay, so you either want to put it's like the information theoretic part, it's like in continuous time, or you want to think of the physical dynamics, it's like in discrete time, so that they're both discrete time or both continuous time. All right, so let me try to introduce some of the players in the game. One of which is this idea of information geometry, which involves the use of differential geometric tools to describe the manifold or probability density functions. And so many inference problems can be cast in this setting. It's like by viewing that as a best approximation problem in some sense. So you could have, for example, parametric families of probability densities, which form an embedded manifold in this space of all density functions at the same support. And then you can introduce coordinates on this, and the natural coordinates, especially in parametric families, is just the parameter values. Whenever you have some sort of parametric representation of a curved manifold, you have a choice in terms of how do you encode the geometry of that space. It's like one very naive, it's like a straightforward way to do this is to just think of those parametric values, it's like as defining some sort of Euclidean space and then using the Euclidean geometry, it's like of that kind of coordinate chart. The problem with that is that oftentimes conflicts, it's like with the intrinsic geometric properties, it's like of these sort of probability manifolds. And so it's oftentimes desirable to formulate, say the optimization problem, your gradient descent problems, in terms of the intrinsic differential geometric structures, it's like on the space of the manifold of probability densities, as opposed to the Euclidean structure, which is induced by the parametric representation. So in any case, it's like associated this idea is sort of various types of differential geometric concepts, like the notion of a Romanian metric, affine connections, and curvature. And they turn out to be related to statistical issues like the asymptotic efficiency of maximum likelihood estimators. Okay, so then the other issue of course is machine learning, again, many cases it's like you can view many machine learning algorithms abstractly as an optimization problem, where you're trying to find some element of a parametric family of probability distributions that predicts the data or is consistent as possible with the data, and you do this by minimizing some sort of mismatch or some sort of loss function. It's like, in order to do that, it's one very natural way to do that is to introduce these notion of divergence or contrast functions, which are asymmetric analogs of distance functions, and they provide a unified way of measuring information, energy, and entropy. So you've probably heard of things like the KL divergence, and we're going to sort of say a little bit more about that in a little bit. But if you have one of these divergence functions, then they induce Romanian metrics and then induce affine connections on this information manifold. And then these differential geometric structures can lead to optimization algorithms on manifolds, which make more sense and which have better sort of convergence properties. As opposed to, again, it's like working this kind of parametric representation, which I alluded to earlier. Okay, and then it's like my main area of research is in what is called discrete mechanics, and it provides a sort of way of discretizing analytical mechanics, in particular Lagrangian and Hamiltonian mechanics, that is structure preserving. It preserves the kind of differential geometric structure, again, which is present in many of these kind of problems. And the way it's going to connect with the other things which I've mentioned in particular is that this notion of a divergence function, it's like information geometry, turns out to have an interesting interpretation as a discrete Lagrangian. And the discrete Lagrangian is going to be a generating function of the symplectic time H flow map of a Lagrangian and Hamiltonian system. So as a consequence of that kind of interpretation, you can then impart a mechanical interpretation to a certain class of machine learning algorithms. And in so doing, you can view these algorithms as sort of the discrete time flows of some continuous underlying mechanical system. All right, so let me briefly say a little bit about divergence functions. So a divergence function is a map. It's like from two copies of the manifold to the non-negative reals. And it is sufficiently differentiable, and it has a bunch of properties. The first of which is that it's non-negative, and it's only equal to 0 if the 2 points are the same. And so you should think of the points here as being probability distributions, right? So and here it's like there's some notation which I should mention. It's like if I do a subscript I mean I differentiate this divergence function with respect to the ith component of the first variable, and then there's a comma j here, and that means I'm differentiating respect to the jth component of the second variable. So there's some sort of mixed derivative property here when evaluated along the diagonal. And then there's this mixed derivative, which is positive definite. This is going to turn out to be our Romanian metric. And then there's this, so this is the notation which I sort of alluded to just now. And so as I said, this divergence functions are sort of pseudo distance functions, but in the sense that they're non-negative, but they don't necessarily have to be symmetric. So if you take the divergence of x comma y, it's not necessarily equal to the divergence of y comma x. Okay. So once you have this divergence function, you can construct a Romanian metric from this. So Romanian metrics obviously are a way of, it's like measuring distance or the size of tangent vectors, and in so doing, it's like allows you to induce a notion of length of curves. And then there are these affine connections, and affine connections are a way to talk about identifying tangent spaces at 2 points on a curved manifold. And sort of say, when two vectors are identified with each other. So in any case, you have this metric tensor, which is given by this mixed second derivative of the divergence. And then you have these two affine connections, which involve these third derivatives. Okay. So there's more than one of these affine connections. And if you know something about Romanian geometry, it's like, for example, things like the Levi-Civita connection, which is the unique sort of torsion-free metric compatible connection. And what it means for a connection to be metric compatible is the following. If you have a connection, then there's a way to essentially parallel transport a vector. It's like along a manifold, along a curve. And what normally happens is like with the Levi-Civita connection is that if you have a pair of vectors and you parallel transport them along some curve, then the Riemannian inner product of those two vectors along the parallel transport is constant. Okay, so that doesn't happen. It's like in this pair of affine connections, but something analogous to it happens, which is the following: that if you have a vector A and a vector B, and you parallel transport one of those vectors by the first connection, and this you parallel transport the second vector by the second connection, then the Riemannian inner product is preserved. Okay, so that's the sense in which these connections are dual to each other. Okay, all right, and then these dual connections, it's like are related to the Levi-Civita connection by, the sort of the defect of it from the Levi-Civita connection is encoded in what's called the skewness tensor or the cubic tensor, depending on which books you read. Okay, and the upshot of this is that the skewness tensor and the metric tensor here are going to show up in an inverse problem where if I give you the metric and I give you this pair of affine connections, is there then a divergence function which induces that? Okay, and that turns out the solution of that problem, that inverse problem, also has a nice mechanical interpretation. All right, so you can ask, well, how do you go about constructing? It's like something with these kind of properties, and one way to do this is to consider what's called the Bregman divergence, which is induced by a strictly convex function, and more or less it's the difference between the value of that convex function at one point and the basically just the first order Taylor approximation of that convex function expanded around a different point. Okay, so that's what this Bregman divergence is. And it's like the familiar KL divergence is an example of a Bregman divergence, and the associated convex function there is the negative Shannon entropy. So if you have the negative Shannon entropy as this convex function, the Bregman divergence, which is induced by that, is the Koblek-Leibler divergence, and then the divergence induces a metric, and that metric is the Fisher-Rao metric. Okay. All right. So that was a brief introduction to information geometry. And then now let me say something about geometric integrators. So geometric integrators are a class of numerical methods that preserve geometric properties. So things like symplecticity, momenta, or what oftentimes happens is that the dynamics of your problem evolve on a curved space. And that curved space might have some structure like a Lie group or homogeneous space structure. And you might want to construct numerical methods which respect that sort of underlying manifold structure as well. And the reason why one is interested in respecting those kind of geometric conservation properties is because obviously if it is a geometric invariant, the dynamics evolves on a level set of that invariant. And so if you have a numerical method which respects that, then oftentimes what happens is that you get better numerical stability and better qualitative agreement with the exact flow, because they're both evolving on the same constraint manifold or invariant manifold in some sense. All right, so let me say a little bit about how you construct these things for mechanical problems. And the way you do this is by sort of considering what's called Hamilton's principle. And Hamilton's principle is a coordinate independent way of describing the dynamics of a mechanical system. So it's stated as follows: if you have an initial point and a final point, then the trajectory a mechanical system actually takes is that which extremizes what is called the action integral, which is the integral of kinetic minus potential energy. And what we mean by extremizing it is that if you look at the trajectory the system actually takes and you were to perturb it slightly while keeping the endpoints fixed, then the action, it's like will sort of be stationary with respect to first order variations. It's like up this curve. Okay, so you can ask, how do I go about discretizing something like that? And one very natural way to discretize that is to imagine having sampling that trajectory. It's like by a bunch of points, and then introducing what is referred to as the discrete Lagrangian, which is you should think of as a piece of the action integral, right? So imagine instead of integrating from time A to time B, you integrate from time A to a small sort of displaced time, and so you just have an action integral now, sort of with two nearby points, and then that is what is that's what is called the exact discrete Lagrangian. It's like it's the action integral evaluated. It's like with those two nearby points along a curve which satisfies the Lagrange equations. Okay, which are the actual equations of motion. So this is a way to formulate, it's like this exact generating function for a symplectic map in terms of what is called Jacobi solution. And Jacobi solution is related to, is a solution of the Hamilton-Jacobi equation. All right. Anyhow, so if you have this discrete Lagrangian, as I said, it's a piece of the action integral. If you imagine summing it all up, it's like these pairs of points, you get something which is an approximation of the action integral over the entire interval. And the discrete version of Hamilton's principle states that that discrete action sum is stationary when you fix the endpoints. Okay, and when you write down then the corresponding stationarity conditions for that discrete Hamilton's principle, you get the following discrete Lagrange equations, and then the D2 here means I'm differentiating with respect to the second slot, and the D1 here means I'm differentiating with respect to the first slot. Okay, so so this turns out to be an equation which implicitly defines a map from pairs of points to pairs of points. From the solution at k-1, it's like to nk, it's like to time k and k+1, if you will. So if you don't like thinking of things in terms of sort of multi-step methods, it's like where you have data at two different times, you can also think of them as a, it's like sort of single time flow map, discrete time flow map, by introducing the momenta, it's like in this way, okay? And then if you know something about symplectic maps, you'll see that this is a characterization of a symplectic map in terms of what are called type 1 generating functions. And so indeed, the discrete Lagrangian is a type 1 generating function of the exact flow. Okay, so anyway, so there's this object that's like which we call discrete Lagrangian, and it's encoding, it's like the dynamics in some discrete sense. And then you can ask, well, can I say something about the properties of the numerical method by analyzing properties of this discrete Lagrangian? And it turns out that you can. And one way you can do this is you can ask, well, what happens if I take this discrete Lagrangian, it's like for a pair of points, and I imagine I say rotate both points by the same rotation matrix. And if the discrete Lagrangian is invariant under this diagonal action of some symmetry group, then there's a discrete momentum map which is preserved by that discrete flow. So in particular, if you have something which is rotationally invariant, then there's an associated angular momentum, it's like which is preserved, for example. So if you had a discrete Lagrangian which was rotationally invariant, then there would be a discrete momentum map which is encoding some sort of discrete notion of angular momentum preservation. Okay, so the other thing you can do, it's like with this discrete Lagrangian, is that you can do error analysis on it. So normally it's like if you have a numerical method, say a Runge-Kutta method, you know, it's like you apply the Taylor expansion on the entire method, and then you try to figure out whether or not it is a good approximation of the Taylor approximation of the flow. So here, you can do something a little bit easier. You can analyze properties of this discrete Lagrangian, which is just a scalar value function. Okay, so if you have a computable discrete Lagrangian and it approximates the exact discrete Lagrangian to a certain order of accuracy, then it turns out that the corresponding numerical method is going to have that same order of accuracy. So it allows you to analyze properties of the numerical method by just analyzing the extent to which this computable discrete Lagrangian approximates the exact discrete Lagrangian, which I talked about earlier. Okay, so that's sort of you know, some of the motivation for why it is that you might want to use what are called variational integrators to construct numerical methods, because they systematically give you something which is symplectic. If the discretization has some sort of symmetry, it's like it preserves momentum as well, and there's a whole body of error analysis that's like built around it. Okay. So the other thing it's like which is of interest is that maybe you're not interested in mechanical systems, and you know, the problems which you work with, it's like don't have you know, it's like mechanical structure. You still might be interested in these kinds of discretizations for the following reason. So you know, critical to many problems, it's like in numerics and machine learning, is this notion of sensitivity analysis, right? So and you've probably, and in fact, it's like things like you know, it's like back propagation is an example of you know, it's like the application of sensitivity, adjoint sensitivity analysis. Okay, so if you have any system of differential equations, then it turns out that the adjoint system has a Hamiltonian structure, even if the original system of equations do not. Okay, and it turns out that preserving symplecticity under discretization then is essential to maintaining this relationship between the primal and adjoint variables. So what do I mean by this? So imagine you have a differential equation and you take the adjoint system, and then you discretize that. Okay, so that gives you sort of essentially, so you first take adjoints and then you discretize. That gives you one way of computing discrete adjoints, so to speak. And then the other thing you could do is you can take that differential equation, discretize it, and then compute its adjoints. Okay, so in general, it's like what you really want to do is to discretize and then take the adjoints. That's really, you know, the sensitivity you care about. But a lot of times people don't like to do that because you have to do something like automatic differentiation in order to compute something like that. So what oftentimes happens instead is that people compute the continuous adjoint equations and then they discretize it using their favorite discretization scheme. But that ends up oftentimes being very problematic because it could very well be that you know, it's like the search directions you end up getting from that kind of adjoint analysis isn't even a descent direction. And so if you're doing things like shooting, it's like for solving 2-point boundary value problems, the method just fails to converge, it's like because you don't even have a descent direction. So in any case, what ends up happening is that this notion of symplectic discretizations is important, turns out to be important. It's like for discretizing adjoints, at least if you want to take this point of view of looking at the continuous adjoint equations and then discretizing it. So more or less, if you want to do that and get the same answer as discretizing and then taking adjoints, you have to discretize that adjoint system with a symplectic method. Okay. All right. So so there's one part which I didn't mention with regards to how you go about constructing these things, which is which is how do you go about constructing it's like a discrete Lagrangian with a certain order of accuracy. And you know, it's like, and more generally, how do you even go about constructing a computable discrete Lagrangian? So I'm going to try to recharacterize the exact discrete Lagrangian in the following variational way. So I'm going to say that the exact discrete Lagrangian is the extremizer of the action integral over the class of curves which are sufficiently differentiable and which satisfy the boundary conditions. So you have Q0 and Q1, and you want to have a curve, it's like Q of t, which agrees with those endpoint conditions, and I want to extremize this action over that family of curves. So this turns out to be equivalent to our previous description because the stationary conditions for this extremization problem is just the Euler-Lagrange equations. So this is equivalent to saying that I have to evaluate the action integral on some curve which satisfies the Euler-Lagrange equations and the boundary conditions, which is how I characterized this exact discrete Lagrangian earlier. But thinking of this exact discrete Lagrangian in this sort of variational way allows me to do the following thing. It allows me to say, well, instead of looking at maybe all twice differentiable curves, let me imagine now looking at some finite dimensional family of functions, say polynomials. And instead of thinking of the integral, I could imagine replacing that integral with some sort of numerical quadrature formula. So if I choose a finite dimensional function space and a quadrature formula, that allows me to rewrite this or approximate this in some sort of computable way. Okay, and this is how you go about constructing one way of constructing a computable discrete Lagrangian. So so with that in mind, it's like then you can ask, well, can I say something about the nice properties of variation of these discrete Lagrangians based on the choice of the function space and the choice of the quadrature rule? And indeed, you can. So if you recall, the first thing I said was that you can construct momentum preserving methods if the discrete Lagrangian is invariant in some sense under group action. So one way you can construct a group invariant discrete Lagrangian is to have a approximation space which is what I call group equivariant. So the idea is the following. Imagine you have a bunch of points and there's a curve, it's like which is associated with those control points. Okay, and now if you take those control points and you rotate all of them and you look at the associated curve, if that's related to the original curve by that same rotation, then we say that my approximation space, my finite dimensional approximation space, is group equivariant. And if you use a group equivariant approximation space to construct this discrete Lagrangian, then you'll get a group invariant discrete Lagrangian. And so this then gives you a way of systematically constructing methods which preserve momentum. Okay. All right. So constructing group equivariant spaces for mechanics problems isn't so hard, but doing this, it's like for space-time problems like partial differential equations takes a bit more effort. But there is we have some ideas about how to do that as well. And then the other property is about this issue of error analysis again, and you can ask the following question, right? So if you have an approximation space and it turns out that the approximation space you choose, it's like has what is called a best approximation error, which is that if you try to find the sort of the closest point projection, it's like of the exact solution, it's like onto this function space, what is the error associated with that? Okay, so this is what's called the best approximation error. And you can ask the following question. If I construct a numerical method, it's using this choice of function space, and I look at the error associated with that, is this error bounded by some constant multiple of this best approximation error? Okay, so, and if you can do that, then it converts the problem of constructing good numerical methods to the problem of constructing good approximation spaces with good best approximation errors. Okay, and this is, for example, the basis behind understanding why spectral methods work so well, because it's like the space of Fourier basis functions are it's like a space that's like which has a best approximation error which decays exponentially as you add more and more terms, at least if the solutions which you're looking at are analytic, right? So anyway, so there's a lot of nice results into our approximation theory which you can leverage if you have this kind of quasi-optimality type result. So it turns out that you can do this kind of variational error analysis, and you can prove that your variational integrator has this kind of quasi-optimality property. And what that allows you to do is to construct integrators which are order optimal. So if you take higher and higher degree polynomials, it's like the variational integrator will converge, it's like at a polynomial rate which increases with the polynomial order, as you would expect. And if you were to keep the time interval fixed but increase the number of terms it's like you have, it's like then you construct what are called spectral variational integrators, and those converge at a geometric rate. Okay. All right, so now it's like, let me sort of try to combine what we had talked about initially, which was information geometry, with variational integrators. Okay, so this is a result by Jin Zhang, it's like, and myself from 2017. So what it says is the following, right? So if you recall, if you have a divergence function, it's like there is a Romanian metric associated with that, and associated with that Romanian metric is some sort of geodesic flow. Okay, so that's some sort of continuous time dynamics which the divergence function induces. But it should be clear, it's like that the divergence function also is a generating function in the sense that it takes two copies of the manifold and it gives you a scale value. It gives you a real number, right? So you can think of it as a generating function in the same way that the discrete Lagrangian is a generating function. So you can ask, if I view this divergence function as a generating function of a symplectic map, is that symplectic map a good approximation of the geodesic flow associated with the Romanian metric, which is induced by the divergence function? Okay, so the upshot of this theorem is the following. It basically says that if you take the divergence function and you scale it by 1 over h, where h is now then interpreted as a time step, right, then that object is going to generate a map, right, which is a good approximation of the time h flow of the geodesic equations. Okay, so it's always consistent, and if it turns out that Bregman divergence if it turns out that divergence function is a Bregman divergence, then it's not only consistent but it's second order accurate. Okay, so in particular, what that means is that if you decided to use KL divergence as a generating function in the sense which we talked about earlier of a map, then that's going to give you a second order accurate discretization of the Fisher-Rao, it's like geodesic flow. Okay. All right. So that's kind of an interesting, it's like observation. And then the other thing, it's like which shows up is that you can ask about this notion of canonical divergences. So if you have a divergence function, it induces a metric and a pair of affine connections. If, on the other hand, I give you a metric and a pair of affine connections, you can ask whether there's an associated divergence to that. Okay, so that's sort of the inverse problem. So it should be clear that this is not unique, but you can still ask, it's like whether you can construct one systematically. And one way to do this is to use Hamilton-Jacobi theory for the following Lagrangian. So you take the metric, you contract it with two velocity vectors, and you take this skewness or sort of cubic tensor and you contract it with three sort of velocity vectors. And this gives you a Lagrangian, and then you can apply Hamilton-Jacobi theory then to construct a generating function. And in particular, you only really need to construct a second order accurate approximation of this generating function in order to construct a canonical divergence. So that's kind of an interesting inverse problem, and the actual computation allows you to leverage all the stuff I talked about earlier about constructing, sufficiently accurate variational integrators.
So Melvin, I have a quick question. If you go back
Sure.
to one slide and show that, so here there is this order of h cube term.
Mm-hmm.
How do I is that the dominating term, or is that something that I should neglect?
Yeah, that's the leading order term, and it tells you that there's that this thing is it's going to induce a second order accurate discretization of the flow of the Romanian sort of geodesic flow, basically, right? So that's the dominant error term, and that dominant error term then tells you how accurate replacing the exact generating function, it's like with this generating function is. I mean, it's like right. I mean, it tells you what the leading error term is. So this is just a local error analysis, and then if you want to look at the error, it's like over a fixed time interval instead. It's like you lose a factor of h, basically, right? So then the global error is h squared.
H squared. Yeah. Okay, makes sense.
Yep. Right. That's a good question. So so now it's like, it's like we've talked about divergence functions, how they're related to it's like discrete Lagrangians in some precise way. You can also ask now, it's like, if I give you a divergence function, can I then construct a discrete flow which is in some sense allows you to incorporate this notion of inference, it's like with data, okay? So let's just imagine that you have a sequence of xi's, which are in some sense your best guess as to what the distribution it's like really is, and then yi's are it's like your sample data, it's like from this unknown distribution which you're trying to approximate, okay? So so given these xi's and yi's, it's like you can measure some sort of mismatch between the estimator, it's like, and the data using, for example, the divergence function. And then because you don't want the estimator to sort of jump around, it's like, very violently, what you might want to do is to add a momentum type term, it's like to regularize the dynamics. And you can do that, it's like by introducing this term which we had seen before. And so this is the net effect of essentially, so let me explain. So this first term is like involves the divergence of two sort of iterates, it's like of your estimate, right? So this is basically penalizing sort of changes in the estimate which are too rapid, if you will. And so this is like a kinetic energy term, a discrete kinetic energy term, and then there's this discrete potential energy term, which is again trying to drive the dynamics towards sort of an estimate which minimizes the mismatch between your model, it's like, and the data, right? So so anyway, so this is sort of one naive way of constructing, it's like a dynamics which, it's like in the absence of any mismatch with the data would just evolve via something like geodesic flow on the information manifold, but otherwise it will try to do, it'll try to move towards a minimum, it's like of the potential energy, which is the divergence, if you will. So this gives you a purely discrete.
A question, just clarification. Is the yi, should I think of yi here as the likelihood of the data?
You should think of the yi as maybe being something like the empirical distribution which is induced by the data up to that point.
Okay.
Yeah, and then it's like, and then xi would be your it's like your candidate approximation of that data, if you will, of the underlying distribution.
Yeah, I guess I'm curious. Would this reduce? So if I minimize this with respect to, so let's fix xi and I minimize with respect to xi plus 1. Would this reduce to Bayes' rule? If I have xi be the prior PDF and yi is the log likelihood of the of the data, and then
Right.
xi plus 1 is the posterior. If I minimize this over xi, would I get exactly Bayes' rule equation?
I'm not sure you'll get exactly the, I mean, it's like Bayes' rule, just because, yeah, I'm not sure what the impact of that kinetic energy term is. One has to work through the details. Yeah, but that's a good question.
Okay, thanks.
Yeah, I need to check that. It's, yep. So anyhow, yeah. So that's sort of a discrete time way of thinking about you know, how one goes about you know, defining some sort of information dynamics, if you will. All right, and so there is this idea in numerical sort of analysis called backward error analysis, and that allows you to then relate this to a continuous time Lagrangian system. And so you can view, you know, this class of learning algorithms as a continuous time dynamical system, if you will. All right. So anyway, so that's sort of you know, something which is speculative. We haven't really sort of, you know, delved as much as we would like to. It's like into this, but I think Nikolai, it's like brings up an interesting question about to what extent this is exactly inducing, it's like sort of Bayes' rule or something which approximates it. Okay, so so let me now switch gears slightly. It's like, but you know, I will circle back and so I can see how it's connected. So so I'm going to talk about accelerator optimization, and you know, again, one motivation for studying optimization problems is that many learning algorithms can be viewed as optimization problems on the space of probability distributions. Okay, so so if you have this minimization problem, it's again, it's convex, and you know, it's like f is a sufficiently differentiable convex function with a unique minimizer, then you might have heard of Nesterov's accelerated gradient method, which is given as follows. And the significance of the accelerated gradient method is that it converges to the global minimizer at a rate which is 1 over k squared, big O 1 over k squared, where k is the number of iterations which you have. Okay, so Nesterov proved that this big O of 1 over k squared rate is optimal for methods which only use information about the gradient of f at consecutive iterates. And this is in contrast to sort of standard gradient descent algorithms, which only converge at big O 1 over k. So there was an interest in trying to understand, it's like, you know, how do you go about generalizing it? Where is all this coming from? And one attempt to do this was due to Su, Boyd, and Candes, where they showed that Nesterov scheme has this continuous time limit given here. And so this is sort of what you might expect, right? It's like, it's a second order differential equation. It's like, which has this kind of gradient descent type term, but it also has this damping term in it, okay? So, so you can ask, well, you know, and this converges, it's like to the minimizer in continuous time at big O 1 over t squared, which is sort of the continuous time analog of what you might expect. So one natural question is to ask, can you construct continuous time flows which converge at an arbitrary rate to the minimizer? So that turns out to be something which can be done. It's like, and it's an approach which is due to Michael Jordan. It's like at Berkeley. So if you know, it's like as before, if you recall that you have this Bregman divergence, then when those 2 points are close together, it's like then it approximates this Hessian metric, which is given here. And you know, it's like so Michael Jordan is again his collaborators has like introduced this idea of a Bregman Lagrangian, a Bregman Hamiltonian, which is given here, and it has a bunch of parameters alpha, beta, and gamma. But you'll see that, you know, it's like its form is sort of at least a bit evocative. It's like you know, of the discrete Lagrangian, which I had sort of introduced earlier for, you know, it's like approximating certain classes of machine learning algorithms. You have a divergence function applied to 2 nearby points, which is like, again, a kinetic energy like term. And then you have a term here, which is associated with the loss function, right? So so in our problem, it's like the loss function was the Bregman divergence of the estimator. It's like in the data. And so that would be our f. And so again, this is sort of similar to what you have here. And the point is that you have a Lagrangian and Hamiltonian formulation. But what's important to note is that the Lagrangian Hamiltonian formulation is time dependent. Okay, and this is going to have implications when you try to discretize it. As I said, it's like, this object has some sort of kinetic energy-like term which involves the divergence function of two nearby points, and then a term which involves the potential. Okay. All right. So under this kind of growth conditions, the solution of the associated all Lagrange equations exhibit this rate of convergence. Okay. And in particular, if you choose alpha, beta, and gamma, it's like this way, which involves p, which is greater than 0, then you can show that that rate of convergence is big O of 1 over t to the p, right? So and so when p is equal to 2, it's like you get basically the Candace sort of discretization or sort of description. It's like of Nesterov, but at least in principle now you have continuous time dynamics which could converge at an arbitrary rate to the minimizer. Okay, so so the problem, as I said, is that because of these alpha, betas, and gammas, it's like the Bregman, Lagrangians, and Hamiltonians are time dependent. And so you have to be very careful when you try to discretize this using symplectic or variational integrators, because essentially symplectic integrators don't exactly preserve the energy. They only preserve what is called a modified energy. And the modified energy depends on the time step you take. So if you change the time step from, it's like from iteration to iteration, then they're all preserving a modified energy, but they're preserving a different modified energy. And so what ends up happening then is the energy, it's like has an error, it's like which ends up growing. So what you can do instead is you can do what is called a Poincare transform. Essentially, this is a way of taking this non-autonomous system and then embedding it into an extended phase space, which makes the problem autonomous. Okay, so that's basically what's happening here. And when you do that, you get sort of these extended equations, one of which is telling you how the time steps are evolving using a monitor function. Okay, and I'm going to, in the interest of time, let's like skip some of the details. It's like, but let me sort of just say that at high level, that if you assume that the original problem is non-degenerate, right, then it's like you can construct a numerical integrator which has nice properties as well. Okay, yeah. So this gives you a way of constructing time-adaptive variational integrators, and so this is just applied to the Kepler two-body problem with different types of monitor functions, and these monitor functions choose the time step for you. And the upshot of this is that you can get numerical methods, it's like which turn out to be more efficient than Sturmer-Villei. And actually, Sturmer-Villei is a surprisingly difficult method to beat because in separable Hamiltonian systems, Sturmer-Villei is explicit. So it's incredibly efficient for many practical problems. And nevertheless, it's like these methods do perform more efficiently. Okay. All right, so let's now try to do this as like for the Bregman Hamiltonian. So you can do this time transformation. And what's interesting about the Bregman Hamiltonian, these P Bregman Hamiltonians, is that they are related to each other by just this time rescaling here, right? So essentially the trajectories are the same, right? The curves, it's like which are taken are the same, irrespective of what P is. And the only difference is that there's this time rescaling, it's like between the different values of P's. So that turns out to be something which you can exploit in order to construct faster numerical methods. So this is just a plot of what happens when you try to look at these time adaptive, it's like discretizations of the Bregman Hamiltonian using the direct discretization, which means that the time steps are fixed, versus this time adaptive discretization which we introduced. And the time adaptive discretizations perform much faster. It's like they converge much faster for the number of iterations which you have. And this is how the convergence rate changes. It's like as you change P, and as you might expect, larger P is, it's like the faster convergence which you have again. And this is where you exploit this sort of rescaling. It's like, I'm not going to worry too much about it. But I think what's interesting is that if you were to compare this to a non-symplectic adaptive Lagrangian method, say RK45 in MATLAB and in sort of ODE 2.3, you'll see that in essence, the direct versus adaptive approach, it's like doesn't matter when you are using already this non-symplectic adaptive RK method, because basically the time steps are already chosen in a way which exploit this scaling. But it's like with the variational discretization, which doesn't do time step control, knowing the right scaling, it's like gives you a much faster rate of convergence, which is perhaps what you would expect. Okay, so you can compare this to Nesterov's accelerated gradient method, and you'll see that again this converges faster than Nesterov. All right, so you can extend this to Romanian manifolds as well. You can do this for the convex case, the weakly quasi-convex case, and strongly convex case, and these are some. So these are the expressions for both the analog of the Bregman Lagrangians and Bregman Hamiltonians. And we applied this to this generalized eigenvalue problem. Again, these Hamiltonian Taylor variational integrators with adaptivity, it's converge extremely fast. All right. And then this is an application to camera pose estimation. We're just trying to find the optimal pose of a camera. All right. So it's so this is just some description of what are called Hamiltonian variational integrators. I'm not going to go into details. Suffice to say that one of the problems is when you write down this Poincare transformed Hamiltonian, that Poincare transformed Hamiltonian is degenerate, which means that there's no Lagrangian analog of that problem. And so traditionally, variational integrators were all constructed on the Lagrangian side, they were all constructed on this side. And Hamiltonian integrators were done by sort of identifying the Lagrangian of a Hamiltonian and then sort of going around this loop this way. And in sort of work which my group developed, there was a way to basically start with a Hamiltonian and construct this type 2 generating function of that Hamiltonian dynamics directly without going to the Lagrangian side. But with the property that if there is hyperregularity, which basically means that the Hamiltonian and Lagrangian theories can, can be identified, then going down directly with our method is equivalent to going around this loop, basically. So, I won't talk about the details, but suffice to say you can do this, and that's basically what we use. It's in discretizing the Poincare transformed Bregman Hamiltonian. Okay, so let me try to summarize now by saying that information geometry provides a differential geometric interpretation of some class of machine learning algorithms. In particular, the divergence function induces a bunch of differential geometric structures on manifolds, on statistical manifolds, and they are related in this precise way to discrete Lagrangians. And so you can view some machine learning algorithms and optimization algorithms in terms of discrete mechanical systems on the space of probability distributions. And you can study accelerator optimization algorithms and their generalizations. It's in terms of Bregman Lagrangians and Hamiltonian dynamics. And you can discretize them using these time-adaptive Hamiltonian variational integrators. So the hope in the longer term is to try to leverage this analogy between mechanics, learning, optimization, and optimal control to construct new techniques for these problems by, again, leveraging what we know about constructing geometric numerical integrators. And so with that, I will stop and I'll be happy to take any questions.
It was a great talk, Melvin. If there is any question from the audience, let's go ahead.
Hi, Melvin. Thanks for the talk. I have a quick question.
You're
So you mentioned that this accelerated optimization can also be extended to the Romanian manifold setting. So what does it require? I mean, do you have to have an analytical form? Is it has to be something that you can describe like a spherical geometry or hyperbolic space? Or it can be something that implicitly define you only need some oracle to give you the, I don't know, exponential map or
right.
Yeah.
So there's the abstract answer to that, right? Which is that if you look at these expressions we had for it's like these Lagrangians and Hamiltonians, those just require that you have a Romanian metric, right? So you just have the standard Romanian manifold setting, and you can prove that the continuous flows have this convergence rate, which we talked about, some generalization of the results you saw before. But there's also the practical question of, just because you have a continuous flow doesn't mean you can efficiently compute an approximation of it, right? So when you want to compute an approximation of this as a way of constructing a practical optimization algorithm formulated on Riemannian manifolds, then as you sort of allude to, you need something which allows you to efficiently, you need something like a retraction, right? Which is a generalization of, which is sort of like a, it's like a relaxation of an exponential map, right? Or you need, some sort of embedded manifold. So if you have an embedded manifold, it's very easy to construct an integrator, which will do what you need. So we have methods which are based on retractions. We have methods which are based on embeddings. We have methods which are based on projection type techniques, right? So it's clearly hard to work with manifolds where you just have, say, an atlas and you have a bunch of charts of this. And that's because in practice, you have to be very careful. It's like when you're working on atlases, particularly with geometric integrators, because it's oftentimes the case that if you naively discretize the dynamics on an atlas of charts, that you have well-defined methods on each of the atlases, but they don't lift to a well-defined numerical method. It's like on the manifold. So more or less, it's like the updates which you define on each chart is not compatible with the change of coordinates, right? So so if you have two charts which are overlapping, then you use the numerical method you've written down. It's like for one of them, and you change coordinates, that's going to give you a method for the other sort of chart which is not compatible with what you had defined there. And if that's the case, then you end up with numerical methods which perform extremely poorly. So you need something which you need a discretization which then is compatible with the change of coordinates. And oftentimes the way to do that, right, requires you to so the way we've done that in many cases is to introduce what we call retraction compatible charts. So if you have a retraction, then there's oftentimes a way to write down a discrete variational problem on the entire manifold, which is well defined and whose local representation on a retraction compatible chart is very simple. Okay. And this generalizes the idea of canonical coordinates of the first kind on B groups, for example. So anyway, yeah. So yeah, that it's one of those the devils in the details kind of thing. It's like where you have to be very careful. It's like when you're working with manifolds which are given to you just with an atlas of charts, yeah. So right. So yeah. So the discretization, in order for the discretization to inherit the kind of good properties you have in the continuous flow, you have to be extremely careful.
Thanks. Yeah, appreciate that. Thank you.
Melvin, I have a small technical question regarding information geometry, like from the first few slides that you show. So you had these properties of KL divergence listed, right? So a few of them, such as the positive semi-infiniteness of this differentiation matrix and so on.
Right.
So I was just wondering, when you do this differential, yeah, right over here. So when you define, when you're taking these partial derivatives, are you, so you sort of are assuming that these distributions are discrete, right?
That's right, yeah.
So is there like a natural continuous analog, or you will always go via, like, suppose your distributions are continuous, which is often the case, then are you going to discretize them and then use this theory, or is there a natural analog of this thing?
Right, now that's a good question. I would say that if you're working with continuous distributions, sort of, it's like if you're working with the infinite dimensional function space setting, then you have to be very careful, right? Because there are functional analytical issues you have to be mindful of. And certainly some of the properties break. So I would say that the finite dimensional case is in fairly good footing, but the extension to infinite dimensions is fraught with potential minefields, right? I mean, so one has to be careful.
Okay.
So if you read Amari's book, you'll see that I would say that the case for continuous distributions is not entirely nailed down. I think one has to be careful.
Okay.
Yeah. So I mean, I would in practice, I think this issue with information geometry is sort of its successes are sort of closely related to the fact that if you look at it's like exponential families and mixture families, it's like they have very nice structures, and so either the primal affine connection or the dual affine connection has a very simple sort of parallel transport to it, right? And that's where it's like most of the successes are. It's like so it's sort of akin to what Yusu was saying. It's like, well, what happens if you don't have an exponential? How do you actually compute with it, right? And so whenever you do sort of differential geometric things, it's and you want to do computation on it, right? Then something like an exponential map is important. It's like in order to make these things practical. And I suspect that something similar happens here. It doesn't have to be as naively simple as what happens. It's like in the exponential families and mixture families, where it's essentially a Euclidean structure. And so I think there is a potential where the kind of tools which we've developed, it's like for constructing numerical methods on sort of more complicated spaces. So again, if it's a Lie group or homogeneous space structure, it's like we know how to work with those things. But if you sort of have something which is a purely Riemannian manifold, then a big part of it is how efficiently you can compute the exponential map. And it's easier if it's embedded, it's like, and things like that, right? But yeah, I mean, it's like, I think the sort of, the full-blown, it's a continuous distribution setting. It's like where you have to worry about the, so the functional analytical issues. I'm not sure that's been fully addressed.
I see. Yeah, but thanks. Yeah, I understand. One other question, which is probably a little ill-formed as well. So you are talking about, so suppose you have parameterized distribution, and you said the parameters are the coordinates of the problem. But then when you go to this information geometry, these are like sort of non-parametric, in the sense that you have these distributions now, and the parameters are somewhere hidden, right? So
right, yeah, you have to, I think the point is that you don't want to necessarily just use the say the Riemannian structure, which is induced by the parameters, if you will, right? So the parameters are basically like a chart, right? So on a chart, you can say, well, you can measure distances by just using the Euclidean distance on that chart. That's clearly one way to do it. Or on that same chart, you can introduce a Romanian metric, right? So in both instances, you have parameters, you have a chart, but in one case, you're just pretending as if it's like the appropriate notion of distance is coming directly from treating that chart as a Euclidean space. And in another case, you are saying that, well, there's a way to coordinatize things, but then based on where you are in that coordinate system, you have different metric tensors, right? So, so I think those are sort of distinct things. It's like, and in information geometry, it's like the idea is that you want to have, again, Riemannian structures which are not necessarily just the Euclidean sort of structure, which is induced by the chart.
I see. Okay, I think we are quite over time now, but this is a very interesting talk. Thanks again for enlightening us, and hopefully you will chat on offline as well regarding.
Yeah, definitely. I look forward to that.
Okay, let's thank Melvin again, and we'll see you all for next month for the next TILOS seminar. Thank you all for coming.
All right, thank you.
Bye.